Oh, hi there. For lesson 6.9 with the cross product, I'm going to remind you about the different models of multiplication. We'll take a look at the formula and maybe just skim through a light proof, and then I want to walk through the examples. I posted or I'll be posting a PDF of a couple of examples because the formula is a bit of a mess, but once you get into a pattern, it's not that hard to pull off. Just check all of your work real careful. So when we have two vectors, we have discovered that we can find a scalar product that's kind of related to this projection in some way, something related to that distance, some sort of idea of repeated addition. That just gives us a measure where it should be maximized when the vectors are pointing in the same direction and minimized when they're perpendicular to each other. We're going to now define more of an area model. So the other way of multiplying these vectors together, kind of like doing our 2 times 3 example with scalars, is thinking about maybe some sort of measure of the area that they would cover. Now the cross product isn't just going to give us this area by default. We'll develop a formula for getting that area, but it's related to that. Okay. For the formula itself, for a bit of a light proof, let me just project what I've got written down here. So we are obviously, I hope, working in at least R3, and since we don't work in R4 in this course, we're only going to see the cross product in R3. Your cross product is going to be perpendicular to the two vectors that you are crossing. In R2, you cannot have a vector that is perpendicular to any two non-collinear vectors in R2. That vector will be going out of R2, which isn't in R2. So two vectors, u and v with components u1, u2, u3, and v1, v2, v3. We want to find all of the vectors w, call it x, y, z, such that u is perpendicular to w and v is also perpendicular to w. So not mutually perpendicular. U and v don't need to be perpendicular, but a vector that is perpendicular to two other vectors. There you go. Look at that. Okay. So the way that we do that is with the dot product. We set u dot w equal to 0 and set v dot w equal to 0. So here's my dot product. The dot product is going to be the sum of the products of corresponding components of the vectors. I set that product equal to 0 and this product equal to 0. Then you do just a bunch of algebra. You basically eliminate x's, and then you eliminate y's, and then you eliminate z's, and you end up with expressions for x and y and z. You isolate, eliminate, and isolate. It's just a lot of messy algebra that you can look for a proof of. It might even be in our textbook. Okay. Well, you end up having to introduce a constant k here. And we define u cross v to be the value of w when k is equal to 1, if that helps. But that's where the formula comes from, where you do the second component of the first vector multiplied by the third component of the second vector minus the third component of the first vector multiplied by the second component of the second vector. I'm 1/3 of the way through the formula and I'm exhausted already. A couple of students have sort of pointed out that to help with memory aids, that this first component of the cross isn't going to have the first components of any of the vectors in there. But I'm not sure if that's going to help you memorize the order here. So let's just go through, well, you know what, let's go through the actual formula itself. The advice I gave you said, if you want to do u cross v, then what you want to do is you list the components of both vectors twice. u1, u2, u3, u1, u2, u3. List out the components of the second vector underneath, v1, v2, v3, v1, v2, v3. Okay? Bad news is we've wasted 2/3 of our time here, because the next thing you want to do is cross out these outside columns. Okay? And then to get your components, you multiply diagonally and then subtract by this product. So my first component of u cross v is going to be u2 multiplied by v3, and then I will subtract u3 multiplied by v2. Okay. For the next component, I'm going to do u3 times v1, u3 v1 minus v3 u1. Yeah. Last one, u1 times v2 subtracted by v1 u2, u1 v2 minus v1 u2. There you go. I'm not going to say it's that easy because it's kind of involved, but my advice would be don't bother trying to memorize this formula. When you need this operation, just use this development with the numbers. Feel free to show this work right on your page as well. So let's find 1, -2, 0, cross 0, -1, 2. I don't think I'm going to find a sketch that useful here. Well, let's find out. Goes forward 1, left 2, up 0. So I guess that's that first vector. Next vector goes forward 0, left 1, up 2. Okay. And if I'm following the right-hand rule here, first vector, second vector, I think my cross is going like in that direction in there somewhere. But I don't know in what octant it's going to be in. Let's try this out. And you know what? Even just doing your rough work right underneath here, I don't think is a bad idea. 1, -2, 0, 1, -2, 0. Those are the components of the first vector listed twice. 0, -1, 2, 0, -1, 2. Components of the second vector listed twice. Just cross out those outside rows. And you might as well show your operations right in here. Now, you might also want to show these operations. These are simple integer operations, but it is very easy to make mistakes with subtractions and with zeros here. So it is not a bad idea to write down that you are doing -2 times 2 minus -1 multiplied by 0, comma, 0 times 0 minus 2 multiplied by 1, comma, 1 multiplied by -1 minus 0 multiplied by -2. This one's a little bit easier because of all the zeros. I'm sure that plenty of you could have done this in your head, but is it worth it? If it means you're going to make a mistake, I don't know, 5% of the time. -4, -2, this is going to be -1. Like that. Okay. Now, the interesting thing is that you should be able to check every single one of these answers by making sure that this vector is perpendicular to this vector and this vector. And maybe the easiest way to show that is with the dot product. If the dot product is given by mag u mag v times the cosine of the angle in between them, then if the angle in between these vectors is 90 degrees, the cosine of 90 degrees is 0. So I would expect the dot product to be 0. Let's find out. Dot, -4, -2, -1. This will be 1 multiplied by -4 plus -2 multiplied by -2 plus 0 multiplied by -1. That's going to be -4 plus 4 plus 0. Hey, what a surprise, it's 0. You don't need to do this every single time, but it might be good practice just so that you keep track of the fact that this cross product is going to be a vector quantity. So these are commas. You're not adding or subtracting or multiplying these answers together. This dot product is going to be a scalar product. So there's no brackets here. This isn't an ordered triplet. Yeah, sure, it's 3 numbers, but the order of those numbers don't matter. You convince yourself, check yourself, and make sure that, well, I don't know, let's just do it real quick here, that the dot of these two vectors should be 0. 0 plus 2 minus 2. Hey, look at that. I wouldn't suggest trying to eyeball the components here. That will just make that dot 0. It's more challenging than you might think, and you'd be expected to use this method anyways. So, okay, try that out. Takes a little bit more practice than the dot product, I think. And don't stress out too much about the sketches. I won't be asking you to draw this accurately. Okay.